Hello everyone, welcome back. Today we are going to talk about heap data structure, one of the most important one for priority-based operations. So if you have heard of priority queues or Dijkstra's algorithm, guess what? They all rely on heap data structures. By the end of this video, you will know what a heap is, how it works, and how to implement it in the code as well. Let's dive in. A heap is a tree-based data structure that maintains a specific order between a child and the parent. It's commonly used when you need to access either the smallest element or the largest element efficiently from a data structure. So what are the properties of this binary tree? So it's always a complete binary tree. What do I mean by that? So here you can see before completing this level 2, it won't start adding nodes to level 3, and also it will go in the same order. So first it will be adding to the left of this, and then right of this, and then left of this node and the right of this node, and again it will start filling the nodes are like children of the nodes one by one from left to right. And also the second property is the heap order property. Here we have shown a representation of a min heap. So you can see that every parent node is less than its children. So you can see 3 is less than 5 and 7, 5 is less than 8 and 6, and 7 is less than 10. So the same thing happens in reverse in max heap. In max heap, every parent will be greater than its children. So that's the only difference. Where are heaps used? Heaps are used in priority queue implementations and to solve the problems like finding kth smallest element, kth largest element in an array or in a collection. And then heap sort algorithm, there is a heap sort algorithm, and then the Dijkstra's algorithm. These are the applications of the heap data structures. So let's say how it works in the data structure now. So there are two operations as I mentioned. So one is the add or the insert operation, and the second one is the pop operation. So in order to support the add or insert operation in the binary tree, whenever I need to add a new element, let's say I want to add an element with 4 into the heap. Now after adding this one, the heap order is not, or the rule doesn't follow the rule that we mentioned. So what we will do is we need to see like bubble it up. So I'll compare this element with the value of its parent, and if the greater than the current value. So now the parent is greater than the current value, so that doesn't satisfy the rule. So now I'll swap both of those. So now this one became parent. So now I'm again comparing the value of this node with its parent, but the parent node's value is less than this node's value. So I won't do anything. So now the order is restored or the rule is restored. So the same way, if I have to implement that using the array data structure, when I have to add a new element, I'll add it to the last position here, add it 4, and then I'll compare it. I'll have to compare this value with its parent. But how do I determine the parent in array data structure? In data structure, we have a simple formula, like I have the indexes maintained here. So what I'll do is current index minus 1 divided by 2. So current index is 6, minus 1, 5. 5 divided by 2, integer division is 2. So the parent of this one is in the index 2. So what is there in the index 2? I'll compare the value of that with the current node. So okay, it is greater than the current node. So I'll swap that value with the current value. Okay, so once this one is done, I'll have to compare it with its parent. So parent of this node with index 2 is like again 2 like index minus 1 divided by 2. So current index is 2, 2 minus 1, 1, 1 divided by 2 is 0. So the parent of this node is here at index 0. So the value of that is less than the current node. So I won't do anything and I'll exit the loop. So that's how I'll implement the insert or add operation. So now the next thing is, how do I pop the minimum value from this data structure? In order to pop the minimum value, what I'll do is, so pop should remove the element as well. As like once it provides the minimum value, it should remove that element from the data structure as well. What I'll do is I'll take this value 3 and keep it aside, and then I'll replace it or swap it with the last element, which is 7. So I'll make this as 7 and I'll delete this node. So once I do that, I'll have, so now the order is again not correct. So I need to bubble it down or heapify it again. So 7, I'll compare it with both of its children. Or first I'll compare it with, compare both of the children and figure out which one is the smaller of them. So now this one is the smallest children. So the smallest should go to the parent among these three. So the smallest is 4 here. So I am swapping 4 with 7. And now the order is again maintained in this among these nodes. Now I have to compare this with its children. It has only one children, which is left child. So it compares the value of this node with its left child, and the order is maintained here. So I won't do anything. In the same way, if I have to return the min element here, what I'll do is the min, I'll mark it as 3. Min is equal to 3, and then I'll swap this element with the element or the last element. Last element here is 7. So I'll swap the value of 7 here, and then I'll have to delete the value of this one. So once I delete this one, now 7 is not at the right place. So I need to move it or bubble it down. How I'll bubble it down? So I'll compare it with the value of its left child and right child. In order to do that, I need to figure out the left child's index and right child's index. Left child's index is current index into 2 plus 1, and right child index is current index into 2 plus 2. So now 2 into 0 plus 1, that is 1. 2 into 0 plus 2, that is 2. So these are the left and right child respectively. So among those two, whichever is the smallest. So the one with the index 2 is the smallest. So I'll swap these two elements. So now this one will become 7 and this element value will become 4. After that, my current node is at index 2. I'll have to compare it with its children. So index 2's left child is at 2 into 2 plus 1, which is 4 plus 1, 5. And its right child is at 6, and there's nothing at 6. So it has only left child. So I'll compare the value of this current node with its left child, and current node value is less than its left child. So the order is preserved. I won't do anything. So that is how we will implement the heap data structure using an array or a array list. Let me explain the code here. So in Java, like I have taken an array list here. So if we take a primitive array, then we had to maintain the storage or the capacity manually. So I have taken an array list, and then I have named it as values, and I have initiated that in the constructor here. And then this is the add method. In the add method, what we should do, we will add the current value first thing. Add will, as I mentioned, add will always insert it in the last as the last element. Like we looked at the example of inserting a 4. Add will insert it here, and or this one 4 is already there. Let's say if we wanted to add 3 again, so add will insert at the last place here, and then we needed to bubble it up. So how the bubble up work? So bubble up, I have implemented a method here. So bubble up will check the current index. What is the current index? I have added to value.size minus 1. So the total size is 7. 0, 1, 2, 3 up to 6, which is 7. 7 minus 1 is 6. So the current index is 6. And what I'll do here. So when the current index is 6, I'm trying to determine, while index is greater than 0, I'll keep repeating it. Like I'll keep bubbling it up until when. So here I'm determining the parent index of the current index. Current index is 6. Index minus 1, 5. 5 by 2 is 2. So parent's index is 2. So value.get of current index is greater than value.get of parent index. If the current index value, let's say if the current index value is greater than its parent index value, so I have added it this way, right? I have added it as this way now. So if the current index value is greater than parent's index value, I can leave it as it is. So I'll break it out. But if the current index value is less than this, then I'll have to swap those two. So current index value is 6 here. Its parent means 6 minus 1 divided by 2. so which is 2 here. So parent index value is greater than this. So I need to swap those two. So 7 will come here and then 3 will go here. So in the same way, so I'll be swapping here also. And then now the current index value is, I'm making it as index is equal to parent index now. Current index value became 2. So now I have to check it with its parent index. So parent index is current index minus 1 divided by 2. Current index is 2 minus 1, 1. 1 divided by 2 is 0. So the parent index is at 0. So I'll compare it with its parent index value. So 3 and 4. So parent index value is, the value at the parent index is greater than the current value. So I need to swap it again. So I'm swapping these two as it is represented here also. Okay. So that is about implementation of add method. So let's see how the pop method works. So for the pop method, as it is shown in the code here, I'm checking if the value is empty. If the array is empty, then I'll be throwing a runtime exception that the heap is empty, because the operation is not supported. When it is empty, I cannot pop anything. Otherwise, I took the min value. Min value is always at the index 0, which is this one. And then what I'm doing is I'm setting the 0th value or the current value with whatever is in the last index. So the last index is value is 7. So I'm replacing it with the value in the last index, and then I'll be removing the last index value. So I'm removing or deleting this node. After this, what I'm doing, I need to bubble it down. So I'm at the current index of 0. I need to bubble it down. So in order to bubble it down, what I'm doing here. So let's look at the bubble down implementation. So my current index is 0, and I'm starting from 0 every time I need to bubble down after the pop. So while index is less than values.size, while index is less than the array, so I'll have to determine the left child and right child, and I need to determine which is smaller of those two. Left child is equal to 2 star index plus 1, and right child is equal to 2 star index plus 2. And if left child is greater than values dot size, I mean the index, left child index is greater than values dot size, I'm just breaking out of the loop. So here in this case, in this specific case, left child is 2 into 0 plus 1 is 1, 2 into 0 plus 2 is 2, is the left child and right child index respectively. So among these two, I'm comparing now here. If right child index so I have just assigned the smallest index as left child index, and also I'm checking if there is a value existing in right child index. If it doesn't exist, anyway I have assigned it as left child index. So if the value exists in the right child index, and if the value at right child index is less than the left child index, then I'm assigning that as the smallest index. Once that is done, I'm comparing it with comparing the parent index, which is the value at this index 0, with smallest of its child's index. So among these two, the right child index or the value at the right child index is the smallest. So I'm comparing it with this. So this value is smaller than the current index value. So I'll have to swap those two. After that, I'm making the current index value is smaller index. So smaller index is 4. So smaller index is 2, sorry. So I swapped that, and now I need to check it with its children. So current index children is again 2x plus 1 is the left child index, 2x plus 2 is the right child index. So this is the left child index, and this is supposed to be nothing. So this is the right child index, and there is nothing in this one. So here, when I don't have anything on the right child, the smallest index is by default the left child. So I am comparing it with the current index value, and it is already greater than the current index. So if the value at the current index is less than the value at the smaller index, then I'm breaking out of this loop. Then the rest of the things are arranged in the order that we expect. So I'm breaking out. And then what happens once I bubble it down, I'll return the minimum that I had kept aside, which is 3. And then there is a peak method I have implemented. This is simple. I won't pop out. It is same as pop, but I won't be removing the minimum node, but I'll be just returning the value of the minimum node, which is the node at the 0th index. And if the value is empty or the array is empty, then I'll just throw the exception. So this is how the heap operations works, and this is how the basic implementation looks like. I hope it is clear. There is nothing complicated here. We just have to remember how the parent index value is calculated here and how the respective left child and right child index is calculated here. That is the key thing. Once that is done, everything else is kind of intuitive and easy. So this is the implementation of min-heap. So I made it integer specific, and there is an implementation which is generic. Like I like this generic representation whenever supported. So in real world application, we might not be dealing with only integer values. We might be dealing with other type of objects like a person or a person where we will have certain criteria for defining greater than or less than, and we have to order it based on that. Maybe it's based on the person's salary, or maybe we need to order the person based on his age or anything. Like we need to return the person with the minimum age or maximum age or anything. Those kind of operations can be performed here, which is helpful. And to represent it in the Java library, we define it as a priority queue. And if we want to create a max heap, then we need to provide this collections.reverse order. So let's say here I have created a priority queue integer min value and max value. So I have added 10, 20, 5, 2 to the min heap, and I have done the same thing, 10, 20, 5, 2 to the max heap. And irrespective of which order I'm adding the element to the priority queue, it should return whenever I query from the min heap or poll from the min heap, it should return the minimum value from the min heap, which is 2. And whenever I'm querying from the max heap or poll from the max heap, it should return the maximum value from the priority queue. So that works as expected, and this is like a Java code. And in order to test my methods also, like I have written certain unit tests. I prefer writing the unit test instead of main methods, just to make sure that, okay, I don't get out of practice here. So here you can see the execution yields the result as expected. And just for reference, for the min integer heap, I have written certain unit tests here. So test for the add method, and there is a test for the pop method and test for the peak method. These are the certain methods, these are certain operations or the implementations that we have written in the min integer heap. So this was about the heap data structure and its implementation, and I spoke a little bit about its applications as well. So if you found this video useful, please like the video, or if there is anything that I can improve, please share the feedback in the comments, and I'll make sure to improve in the next ones. Please do share your thoughts, and I'll see you in the next video. Until then, stay curious. See you.